Now I want to discuss a rather interesting integral. So the claim is like this. Take the integral from x equals minus infinity to plus infinity e to the minus x squared dx. That's equal to the square root of pi. So how can we prove this? So firstly we'll just introduce a notation. We're going to write I for this integral that we're talking about. Okay, so we want to prove that I is equal to the square root of pi, or in other words that I squared is equal to pi. Okay, so let's think about I squared. Okay, so here's I. And then we want to multiply it by the same thing. So we're going to do the same thing, but this time we're just going to write it with a different variable. It's the same integral, but we just renamed the variable as y. Okay? So that's our I squared. Now the thing is, you see we've got x and y both running from minus infinity to plus infinity, so that's the same thing as doing a double integral over the whole plane. Over the whole xy plane, where x and y are both running from minus infinity to plus infinity. And then e to the minus x squared times e to the minus y squared, that's e to the minus x squared plus y squared, dx dy. So now the cunning thing that we do now is we're going to rewrite this in polar coordinates. Instead of describing the plane using Cartesian coordinates x and y, we're going to describe it using polar coordinates r and theta. Okay. So our r, that's going to go from 0 to infinity. R, remember, is just the distance from the origin. That can be anything between 0 and infinity. And then the other polar coordinate is theta. Theta goes from 0 to 2 pi. And then what are we integrating? Well, here we've got x squared plus y squared. Now x squared plus y squared is the square of the distance from the origin by Pythagoras, but the distance from the origin is called r, so this we can write as e to the minus r squared. And then here we've got dx dy. So what do we do with that? Okay, so that's just the element of area, the area of a small piece of the plane. And standard thing about integration in polar coordinates, that the area element can be written as r d theta dr. And this is the element of area. Okay. So this is good because, you know, we wanted our answer, we wanted I squared to be equal to pi, and now we begin to see where a pi can come in because we've got this theta here. Now actually you see this inner integral with respect to theta. This is extremely easy because the e to the minus r squared r doesn't depend on theta, so it's just basically integrating a constant. So all we get is just an extra factor of 2 pi. So we've got the integral from r is 0 to infinity. And then the inner thing is just giving us a 2 pi. And then we've got e to the minus r squared, r dr. Okay. So this we can do by substitution. We're going to substitute u as r squared. So du is 2r dr. So what we've got here, so we have to substitute in the limits, but r is 0 corresponds to u is 0 because u is just r squared, and r is infinity also corresponds to u is infinity. And then here we've got this factor of pi, and then we've got a 2r dr, which we said is the same as du, and then the e to the minus r squared, that's e to the minus u du. Okay, so now this is not such a hard integral. Indefinite integral of e to the minus u is minus e to the minus u, so here we've got minus pi e to the minus u, a change in that from 0, u is 0, all the way up to u is infinity. Okay, and now at infinity, e to the minus u is going to 0, so we've got a 0 here, and then at the bottom we've got a minus pi, and then e to the minus 0, but e to the minus 0 is just equal to 1, so it's like that. So altogether we just get pi. So we've proved that I squared is pi. And of course I is positive, I is an integral of positive things, so it must be positive. No ambiguity about the sign. I has got to be equal to the square root of pi, which is what we were supposed to prove.